Hello, my name is Schimek.
And I'm Isabel Biol, and today we're going to talk about AtLAST. First, Alice is going to present why we needed a new telescope, and then I'm going to talk about how we are going to make it into a more sustainable telescope.
So what actually is AtLAST? AtLAST is a design study at the moment. It's the concept for a new 50-meter single-dish sub-millimeter telescope, which will cover the same frequencies as ALMA. And the special thing is it will be, or we plan to power it with renewable energy. AtLAST will be particularly good to detect extended and faint structures in contrast to ALMA, which is an interferometer, and we've filtered out. And I'm going to explain why now. So when you have a single dish facility, which is one single dish, it's quite big usually, and we have low resolution, but we have a large field of view, so we can map the whole sky. Well, when we have an interferometer, we have a lot of smaller dishes, so they can go away from each other. We have quite a high resolution, but therefore we also don't have the field of view. So it's really good for follow-up studies, detailed studies, but we can't actually survey with interferometers. So there's a thing called source starvation, where when we have interferometers, we just run out of sources to observe because we don't actually have big surveys to find the sources we want to look at in detail. So this is where single dish facilities come in, where we have big field of views. We can just map out the whole sky. And you can see an example for this, for example, in here. This is an apex observation where we have a big field of view, the whole sky, and all these little dots are high redshift galaxies that were found. And you can also see it a bit more zoomed in here. These are single dish observations. You can see it's not well resolved. You see just blobs basically, but this is how we find it. And then when we do follow-up studies with ALMA, we can actually resolve the sources in more detail. Another problem that we have with interferometers is the so-called missing flux problem, which is just an intrinsic thing of interferometers where we filter out diffuse large-scale structures when we observe. So this is also something, if we want to observe these large-scale structures, we need single-dish facilities. So what makes AtLAST unique? Because we have a lot of single dish facilities. We have IRAM, we have Apex. So why would you need it? For example, AtLAST is going to be really, really big, 50-meter single dish telescope. This is bigger than ELT. This is the LMT is similar in the size, but it's really big. But also we don't only have a big mirror, we have also a large field of view. You can see us here, we have 2 degrees field of view. So together with a big field of view and a big dish, we can calculate what's called the throughput, which basically tells us how good the mapping speed of the telescope is going to be. So a high throughput means that we can actually do surveys extremely well. And you can see AtLAST here. This is the year versus the throughput. We are better than we're going to be better than any facility that's on the market right now. So if we want to do big surveys of the sub-millimeter sky, this is perfect. So this brings me to the science goals of AtLAST, because there are lots of different goals. We have actually a large international community working on the science goals, everything from solar physics to cosmology. And here I'm showing just 4 of the main science drivers that we have, which is first of all the galactic plane. We want to look at the Milky Way galaxy. We want to look at the hidden circumgalactic medium, which is the area around galaxies, the fuzzy things in the halos. We want to also make, as I said, a really big survey like the SDSS survey, but in the sub-millimeter. And we also want to look at the spatially resolved asset effect. The sub-millimeter in general is a really good way to study the coldest and densest areas in the universe. In galaxies, this is where stars are formed, where planets are formed. So if you want to understand the formation of solar systems, we want to look at this. Also, when we go at the higher redshifts, the very prominent infrared lines are shifted into the sub-millimeter. So if we want to look at these lines at high redshift, this is also very good to look at. Here we see an example of what I mean when I say we want to see large-scale structures. The first image here, it's a simulation of a big galaxy. And these 3 are just the simulation put into simulators for telescopes. So this is basically a toy model, what AtLAST would be like. It's an ALMA antenna, but it's 50 meters big. Here we have ACA and here we have ALMA. And all have the same observing time. And you can see that we actually recover the large-scale structure of the galaxy if we look at it with the 50-meter telescope Well, with ACA, we don't really see anything. And with ALMA, we only see like the most bright structures, but we don't recover most of the flux that we see. And this is, first of all, as I said, the missing flux problem that we just with interferometers filter out the emission, but also because this is a mosaic detection. So with if we have a bigger field of view, we don't actually need many pointings. So we can actually use the observation time that we have for just having a deep observation of ALMA. In the same time, we have to do lots of different pointings. So the absolute time we observe per pointing is far less. So you can do deeper observations with a single dish facility also.
Nice. And here's where I take over. So why is AtLAST important for this meeting today, and what do we do in sustainability? We are the first telescope. We are currently in the design phase, and we are the first ones to already here implement ideas and designs for renewable energies to fuel this telescope, which means in sustainability development goals, we are really working on the affordable and clean energy, and we are trying to lower the carbon footprints of astronomy. And that's why also we are funded under the EU's Horizon Call for more sustainable research infrastructures. When we talk about why this is needed in astronomy, we talk a lot about flights in general, but also ground-based telescopes are a big part of the astronomy's carbon footprint. About 13% of a normal astronomer's footprint stems from these telescopes that they use. And we have a carbon intensity of 24 tons of carbon dioxide per paper published when such a telescope is used. Some telescopes in the Atacama have already implemented some solar energy or have connected to the national power grid, but all those still obviously have quite some carbon footprint just because they still use carbon in these systems. So what are we going to do? As Alice said, we're going to be big. 50 meters is kind of hard to look at, but if we just compare it to the other telescopes, we can see how big AtLAST will be. And also its demand will be quite substantial with 1 to 3 megawatts projected. That is a small city. So we are looking in power sources that we can use on site. Wind doesn't work. It's not really windy up there. However, we have one of the best solar sources on the planet at the AtLAST location. You can see here the Chilean summer, the winter, and just for comparison, we are currently sitting in Oslo. This is the solar radiation here in Norway. So sun is great. You can generate power with photovoltaic arrays or with concentrated solar power systems. And I have recently conducted a study, techno-economically, to check what combination of different power system components would be cheapest and what carbon emissions would happen to employ for this telescope. This is our model. You can absolutely use it yourself. Down here is the open source GitHub. And when we check this optimization for 2030, we see that actually the cheapest system that we find has mostly photovoltaics in it, uses batteries and hydrogen when during non-sunny periods. And then we have some diesel generation here in gray, which is used for consecutive cloudy periods, just because bigger battery parks actually would be more expensive than using a diesel source here. We can see levelized costs of electricity of around $116 per megawatt hour. Recently in Europe, we have seen up to 500. So, you know, this is cheap. This is good. We want this. Yes. Comparing carbon footprints, this would be a business as usual, just diesel. And we save about 95% of the carbon footprint of this power system when we would employ such a system here. That's substantial. So what else are we going to do? We are also looking in energy justice and in cooperating with people close by. We have a number of telescopes that are situated close to where we want to build AtLAST. There's a city, and there actually is also a utility that is giving power to the city. So recently we have visited San Pedro de Atacama and held community workshops with inhabitants, with the community, just to see what their wishes are. They also would like to shift to more renewable energies. We could collaborate there. We have visited a new photovoltaic park that this utility that is mostly using diesel generators also is currently building. And then we checked out Alma's gas turbines. They are gigantic. Alma is also very big, not a single dish, multiple dishes. And they are having 3 very big diesel gas turbines operating here for this. So I just want to remind all of us that are here present today, for sustainability development goals, it's super important to work together, to collaborate, because as I mentioned, we are working here on the affordable and clean energy, but we can absolutely also talk to others and work together with others for sustainable cities and communities, for climate action. And then in overall, we will have better partnerships and more collaboration for the goal of more sustainability on this planet. That's it from me. Super excited about the discussion to come.
Thank you very much for listening.